So we're going to discuss music in this lesson. A lot of the stuff is to do with the standing waves from before. For example, here is a guitar, and this is fixed on this side, and it's fixed on the other side, fixed on both ends. It creates the standing waves. You can be able to calculate the frequencies. You can calculate everything that you need for this stuff. So we will talk about that today. If you want to know how pitch is controlled, we can tighten this, which changes the length of the string or even the tightness of the string. That affects the pitch. Okay, so the title is Music. We'll classify some instruments, investigate the physics of music, understand some things like resonance, and find the resonating lengths and wavelengths. So just remember, for pipes, there are two types, closed and open pipes when we're talking about musical instruments. We of course have the stringed instruments, which is closed on both sides, which is self-explanatory, like a guitar. But when we're talking about pipes, closed pipes, which means one end is closed, one end is open, like a bottle, or a clarinet, or a saxophone. You could even use an organ pipe as well. An open pipe which has two holes, so you can see that here and here, they're both open. And that is something like a flute, trumpet, trombone, tuba, anything like this. Here are some key words that you need to know for this topic. We need to know resonance. You can check it out here. If you click on the link in the PowerPoint, it will take you to it. You have resonance. We have dissonance, consonance. Just as a quick rundown, this resonance is talking about when the vibration of one wave comes and it meets the natural frequency, it will get louder and louder and louder very nicely. So this is good. So where you get the standing waves. A standing waves causes this resonance. Dissonance is when the pitch does not sound good. Consonance is when it does sound good. Timbre just tells us about the quality of the sound, whether it's good or bad. Tension of the spring, just how tight the spring is. Octave is the ratio of the two different frequencies, so it tells you how high pitched it can be or how low pitched it can be in certain sections. Beats is when you have two frequencies that match perfectly, and if they're in line with each other, it is called a beat. You have a noise wave, which is like a wave that shows all the noises of all the different instruments in a sound. You just see everything in one go. And of course, we've done harmonic and fundamental as well. The harmonic is a multiple of this fundamental, and the fundamental, if you remember, is the first standing wave that you get. And then a harmonic is every next standing wave after that, any multiple, times 2, times 3, times 4, like this. This is the noise wave I was telling you about. You'll see a random waveform, lots of stuff going on, and it looks just like noise. And this is resonance. I've mentioned standing waves can cause resonance. It's because it matches its natural frequency. Amplitude of the vibrations will be quite large. So if you were to calculate anything, if you'd be asked to find a standing wave in an instrument or an air column, which in this case, for example, would be open on both ends, like a flute as I was mentioning, you will see that it'll be open here, and you can see there's a half a wave. This is just like the standing wave that we've done. I've already made a video on this, but to run through this, you can see that this is half a wave. So the length is half a wave, half of lambda. So we can rearrange that. So that means a one full wavelength will be double that length, 2L. Keep going here. This is a full wave, yeah? So this length is a full wave. I can say 2 over 2, like that. Yeah, which is the same as lambda. It doesn't matter. 2 over 2 is just 1. That's the same thing. And then you can keep going. You can see how many waves we have. This is 1 and a half. 1 and a half. Okay, so it'll be 3 over 2. 3 over 2 lambda. Swap it around, of course, when you rearrange. For lambda, it becomes 2 over 3. So this is how we got the first rule. Lambda is 2L over N. You can change this around to get L itself. You can actually say L equals N lambda over 2. N over 2, a half, 1 over 2, 2 over 2, 3 over 2, 4 over 2, 5 over 2. Every frequency, every harmonic. So this would be the first frequency, second, third, and so forth. Okay, it can happen in any one of these. Really easy. You could calculate the frequency after solving this. You could just do frequency is V over lambda. So you don't need to worry about anything else. These are the rules that you need. This one and this one. We can use these two. This is just a rearrangement, and that's just a combination. Okay, if you knew the first harmonic, let's say it was 10 hertz, that means you can easily find the second and the third and the fourth. Just times it. Times it by 2, that'll become 20 hertz. Times it by 3 will become 30 hertz. Times it by 5 will be 50 hertz. If I knew the fifth, which said 50 hertz, I could take the 50 hertz and I could just divide that by 5, and that will tell me the fundamental, which is 10 again. So that means I can work both ways. I can find the fundamental if I know which standing wave I am on, or I can find the harmonic if I know the fundamental. Easy stuff. Closed at one end is the other one. Closed at one end is when you have it here. This is a node and it finishes at an antinode, and you can see that this is actually 1/4 of a wave, not half a wave, it's 1/4 of a wave. The next one along, if you were to draw it, you will have your node here, you have your quarter which finishes up. The next half, the next part, will actually bring it down to here. Then that's a problem, because this is another node. I cannot stop at a node. This is fixed on both ends. Not good. I cannot do that. I have to keep going. I have to keep going until I finish at an antinode. Because remember, it's open on one side, fixed on the left, fine. So you will keep drawing the wave until you finish at an antinode, which is open, which is why we have this one. This is the first harmonic. This is the third harmonic. So you notice we've skipped number 2. And then the same thing will happen. If I was to go to the fourth harmonic, if I tried the fourth one, I will go all the way up, down, all the way, and I'll be back here again. Back to the middle. Not allowed, because we have 2 nodes. Not good. So we have to skip the fourth, we end up on the fifth. So counting this is 1/4. This is a quarter, a half, and then you have 3/4. So this will be 3/4 lambda. Skipping number 4, 5, there is 1 1/4. 1 1/4, we can call that 5/4 because we have 5 quarters. And then you can rearrange. So 1/4 rearranged, it becomes 4. 3/4 becomes 4/3. 4/5, like this. And that's how you get the formula 4L/n. If you wanted the length, rearrange, of course, same idea, n lambda over, in this case now, 4. So the difference between closed and open is that in closed, it's a quarter, so 4 is in the formula. In open, it is a half, so 2 is in the formula. Formula is exactly the same, except the number has changed from a 2 to a 4. So the harmonics in closed at one end is only the first, the third, the fifth, every odd number. 7, 9, 11, like this. You skip the even numbers. Okay, so don't get falling into that trap where it asks you for the second harmonic for closed at one end. It does not exist. Now you can also find the wavelength and speed of sound in a closed pipe. Using a simple rule, LB minus LA equals a half lambda. So if you want the wavelength, you take the half to the side. It says the wavelength is 2 LB minus LA, the big length minus the small length. And then you can calculate the speed by using F lambda again. And I did some examples with you using this one here. If you wanted to find the speed of sound, it says originally, first of all, the speed of temperature, we know it should be 347. But we want to know whether the temperature is warmer or cooler, because we need to know the speed of sound. Okay, so we have a frequency, we have 2 distances. Okay, 2 distances, we will subtract the 2 to find the wavelength. Yeah, remember that? V equals F lambda. Let's figure out lambda now by using the new rule, 2 LB minus LA. 2, subtract the 2 numbers. These are in centimeters. I cannot use it. I must divide by 100. I must also divide this one by 100. If I do that, I will get the answer in meters. So that becomes 0.21. This becomes 0.65, 3 at the end. like this. Subtract the 2, you get 0.886 after you do the multiplying. Now that I know this, I'll put that into my formula. F lambda. F392, lambda is 0.886. My speed is 347, which is higher than 343, which means it is hotter. You can actually calculate the temperature by knowing that it goes up by 0.6, but we don't need to do that. You just need to know it's hotter. Okay, easy stuff. Beats when two frequencies match perfectly. So if this is 100 hertz, for example, this is also 100 hertz, you will end up getting 0. This is a beat. There's some practice questions on quizzes. There are some book problems you can do in the textbook. You can get that from LMS. And there's some further reading. You can click on this link. You'll see some text that will explain this to you. And there's some more practice examples on that. Thank you.